Most people think uncertainty is a limitation, a flaw in our measurements, a gap in our knowledge. If our instruments were perfect, if our observations were precise enough, we imagine uncertainty would disappear. Reality would reveal itself completely. Every particle would have an exact position. Every motion would have an exact cause. Nothing would remain hidden. But quantum mechanics does not describe uncertainty that way. The uncertainty principle is not about imperfect technology. It is not about human ignorance. And it is not a temporary problem waiting to be solved. It appears to be woven into the structure of reality itself. The strange part is that this principle does not emerge from complexity. It emerges from simplicity, from the mathematical framework that successfully predicts the behavior of nature at its smallest scales. And once you see what it actually says, something subtle changes. The world no longer looks like a collection of objects carrying hidden properties. It begins to look like something far less intuitive and far more interesting. Our everyday experience teaches us a simple lesson. Objects exist somewhere. They move through space. They possess properties whether we observe them or not. A car has a position and a speed. A baseball has a trajectory. A planet follows an orbit. Even if we are not looking, we assume those properties remain defined. Classical physics reinforced this intuition. In Newton's universe, every particle possesses a precise position and momentum at every moment. If an intelligence knew all those values perfectly, it could calculate the future indefinitely. The universe would be predictable, not practically, but in principle. Uncertainty would merely reflect incomplete information. The world itself would remain perfectly defined beneath our ignorance. This picture feels natural because it works extraordinarily well at large scales. But when physicists began investigating atoms and subatomic particles, something unexpected appeared. The mathematics that successfully described experiments no longer resembled classical trajectories. Particles did not behave like tiny billiard balls. They behaved according to wave functions, and wave functions introduced a completely different structure. To understand why, consider something familiar: a wave on water. A wave is not located at a single point. It extends across a region. Different locations contain different amplitudes. The wave is spread out. Quantum objects are not water waves, but mathematically, their descriptions possess similar characteristics. A quantum particle is associated with a wave function. That wave function encodes the probabilities of possible measurement outcomes. And here, a tension emerges. The more localized a wave becomes, the more complicated its structure must be. A perfectly sharp location requires combining many different wavelengths together. A broad, smooth wave contains fewer wavelength components. This relationship is not unique to quantum mechanics. It appears throughout mathematics. In acoustics, signal processing, Fourier analysis. A short pulse of sound contains many frequencies. A pure musical note contains one dominant frequency but is spread out in time. Precision in one description creates spread in another. Quantum mechanics inherits this structure. Position and momentum are connected through the mathematics of the wave function. And because of that connection, they cannot both become arbitrarily precise at the same time. This is not a statement about measurement errors. It exists before any measurement occurs. The wave function itself contains the limitation. The sharper the position becomes, the broader the range of possible momenta. The sharper the momentum becomes, the less localized the position. The uncertainty principle emerges directly from this relationship, not as an added rule, not as a philosophical interpretation, but as a mathematical consequence of the framework itself. At first glance, this sounds abstract, but experiments reveal its physical reality. Imagine trying to determine the position of an electron. To see something, light must interact with it. The shorter the wavelength of light, the more precisely position can be resolved. But shorter wavelengths carry greater momentum. When such photons interact with the electron, they disturb its motion. Historically, this thought experiment helped illustrate the principle. Yet the deeper point is even more surprising. The uncertainty would remain even without this disturbance, because the uncertainty is already present in the quantum state. Measurement reveals it. Measurement does not create it. This distinction matters because it shifts the question. The uncertainty principle is not telling us that reality hides exact values from us. It is suggesting that exact values of certain pairs of properties may not simultaneously exist in the classical sense we imagine. And that idea is profoundly different. The double-slit experiment makes this tension impossible to ignore. Electrons can be sent toward two narrow openings one at a time. If they behaved like classical particles, we would expect two clusters to appear on the screen. Instead, an interference pattern emerges, a pattern associated with waves. The electron behaves as though multiple possibilities contribute simultaneously. The wave function evolves according to precise mathematical rules. Yet when detection occurs, a single outcome appears. The uncertainty principle sits quietly inside this process. A narrow slit constrains position. As the particle passes through, its position becomes more localized, but the wave spreads afterward. The distribution of possible momenta widens. The resulting pattern is not a technical defect. It is the physical manifestation of uncertainty. The more tightly position is constrained, the more momentum spreads. Nature responds to localization with dispersion. This behavior has been observed repeatedly, not only with electrons, with photons, atoms, molecules. The uncertainty principle is not a peculiarity of one experiment. It is embedded throughout quantum phenomena, and it influences far more than measurements. Without uncertainty, atoms themselves would not be stable. Imagine forcing an electron into an extremely tiny region around an atomic nucleus. A highly precise position would imply enormous momentum uncertainty. The electron's energy would increase dramatically. Quantum systems naturally settle into states balancing these constraints. The size of atoms, the structure of matter, and much of chemistry emerge from this relationship. The principle often sounds like a limitation. In reality, it helps create the world we experience. Matter possesses structure partly because uncertainty prevents certain forms of collapse. What first appears restrictive becomes constructive. The universe is not struggling against uncertainty, it operates through it. This is where intuition begins to fail. We instinctively picture particles carrying hidden coordinates and velocities. Quantum mechanics encourages a different perspective. The wave function does not resemble a classical object with undisclosed details. It describes a range of possibilities whose probabilities evolve predictably. Experiments consistently agree with those predictions. What remains debated is how best to interpret that description. Some approaches suggest that properties become definite through measurement interactions. Others describe branching histories. Still others treat the wave function primarily as a tool for predicting observations. These interpretations differ philosophically, yet all of them retain the uncertainty principle. No interpretation restores the classical picture in which position and momentum possess arbitrarily precise, simultaneous values. The mathematics refuses to allow it. Notice what has happened. Classical physics encouraged us to think of knowledge as incomplete access to an already defined reality. Quantum mechanics does not always fit that model. Sometimes the issue is not hidden information. Sometimes the structure itself differs. The distinction seems subtle, but its consequences are enormous. Consider a map. A map can emphasize roads or terrain. Adding detail in one aspect may reduce clarity in another. Different representations reveal different features. Quantum mechanics suggests something deeper. Position and momentum are not merely two descriptions of the same fully specified object. They are complementary aspects connected by fundamental constraints. Increasing precision in one necessarily changes what can be said about the other. Reality resists being compressed into a single classical picture, and uncertainty extends beyond position and momentum. Energy and time exhibit related relationships. Various quantum observables possess similar constraints. The pattern appears repeatedly. Nature does not present every property simultaneously with unlimited precision. The world remains lawful, predictable in well-defined ways, but not according to classical expectations. This is one reason quantum mechanics feels unsettling. It does not replace certainty with chaos. It replaces one type of certainty with another. The equations remain extraordinarily precise. Predictions can be tested to astonishing accuracy. Yet the structure of what can be known is different from what intuition suggests. The uncertainty principle is therefore not about disorder. It is about limits built into description itself. A reminder that reality is not obligated to conform to the categories that evolved from everyday experience. The microscopic world operates according to deeper rules. Rules that remain consistent. Rules that remain measurable. But rules that do not preserve every classical assumption. And perhaps the most surprising consequence is that uncertainty does not weaken physics. It strengthens it, because it reveals that the theory is describing something genuine about nature, not merely something about our instruments. For centuries, knowledge seemed to move in one direction. Measure more carefully, reduce uncertainty, approach complete description. The uncertainty principle interrupts that narrative, not by introducing ignorance, by revealing structure. There are questions that nature allows us to ask simultaneously with increasing precision, and there are questions linked by unavoidable trade-offs. The limitation is not technological. It survives every improvement, every new detector, every increase in experimental accuracy. The principle remains, not as a barrier placed between us and reality, but as part of reality itself. This creates a subtle shift in perspective. We often imagine that deeper understanding means uncovering hidden layers beneath appearances. A particle has a true position, a true momentum, a true trajectory. We simply need better tools to reveal them. Quantum mechanics suggests that this expectation may be inherited from the macroscopic world rather than demanded by nature. At atomic scales, the framework that best describes observations is not built from definite trajectories. It is built from evolving probabilities and measurable relationships. The uncertainty principle emerges naturally from that framework, not as an exception, as a consequence. This does not make reality vague. That is a common misunderstanding. Quantum mechanics is arguably the most successful predictive theory ever developed. Its calculations agree with experiments to extraordinary precision. Nothing about the uncertainty principle introduces randomness into the equations themselves. The mathematical evolution of the wave function remains highly constrained. What changes is the kind of description available. The universe is not becoming less structured. Our assumptions about structure are being revised. This distinction matters because uncertainty is often interpreted psychologically as discomfort, as incompleteness, as something waiting to be eliminated. Physics points elsewhere. The uncertainty principle has survived every challenge for nearly a century, not because physicists lack imagination, because nature continues to behave this way, again and again. Across laboratories, across technologies, across scales where quantum effects dominate, and modern technology depends on it. Semiconductors, lasers, magnetic resonance imaging, quantum devices. These are not applications built despite quantum uncertainty. They are applications built because quantum uncertainty accurately describes reality. The principle is not a philosophical curiosity. It is experimentally embedded in the functioning of the physical world. Yet, its deepest significance may not be technological. It may be conceptual. The uncertainty principle challenges a very old assumption, that reality consists of objects carrying fully specified properties at all times. At large scales, this approximation works remarkably well. A baseball has a meaningful position and velocity. A planet follows a meaningful orbit. Classical descriptions emerge because quantum uncertainties become negligible compared to the scales involved. But the approximation is not the foundation. It is the consequence. The deeper framework is quantum, and within that framework, certainty and uncertainty are not opposites. They are partners. The more tightly one aspect is defined, the broader another becomes. Precision itself creates limitation. The relationship is mathematical, physical, unavoidable. Perhaps this is why the uncertainty principle remains so memorable. Not because it introduces mystery, but because it reveals a different kind of order. An order that does not match intuition. An order hidden beneath familiar experience. We began with a simple belief that uncertainty reflects ignorance, that reality possesses exact details waiting to be discovered, that perfect knowledge would eliminate every ambiguity. Quantum mechanics did not simply add complications to that picture, it transformed it. The uncertainty principle does not tell us that reality is unknowable. It tells us that knowability has structure, that information is constrained by the way nature is organized. And once that idea settles in, the world looks slightly different. Not less real, not less precise, but less like a collection of perfectly defined objects moving through a fixed stage, and more like a network of possibilities governed by deep mathematical relationships. The closer physics moves toward the foundations of reality, the less certainty resembles possession, and the more it resembles balance. A balance between what can be localized and what can be predicted, between description and limitation, between complementary ways of seeing the same underlying world. Perhaps the uncertainty principle is not ultimately about what reality hides. Perhaps it is about what reality is. And if one of the deepest principles in physics arises not from ignorance, but from structure, then understanding the universe may require more than gathering information. It may require learning that some of our most intuitive questions already assume a world that never existed.